Hello everyone, I'm Jen from Rice University. I'm here to talk about our work on low-cost soil sensing using Wi-Fi signals. This work was done as part of the FarmBeats project when I worked at Microsoft with Revere. We care about soil sensing because it's a key component in data-driven agriculture, which has been proved by agricultural researchers to have tremendous benefits. It helps improve yield, reduces waste in resources, and improves the sustainability for environment. There's a wide deployment of sensors across farms. Data from these sensors are combined together to generate heat maps that can provide further insights to farmers. The wide sensor deployment results in a high cost of data collection, which has become a major challenge for farmers to adopt data-driven agriculture. The data collection cost is contributed by many factors, including the cost of individual sensors, density of sensor deployment, and networking costs for sending data to the cloud. Our work focuses on reducing the cost of individual sensors to make it easier for farmers to adopt data-driven agriculture. We look at two types of sensors for soil moisture and EC. Soil moisture is a crucial parameter to manage water resource, and soil EC is important to monitor soil health and improve crop yield. The challenge is that moisture and EC sensors applicable for data-driven agriculture are very expensive. They are typically between hundreds to thousands of US dollars. There exist cheap hobby sensors that cost less than $20. However, they are not reliable and they degrade fast. Therefore, they are not suitable for data-driven agriculture. The question is, can we reduce the cost while achieving good accuracy for soil sensing? Our idea is to use RF signals. The key insight is that when RF wave propagates in soil, it has a slow speed and a higher attenuation than in the air. The slow speed is caused by soil's higher dielectric permittivity, which is an indicator of soil moisture. And the higher attenuation is caused by the extra transmission loss in soil, which is a function of soil EC. There are some existing RF-based soil sensing systems, such as ground-penetrating radar and time-domain reflectometry. These systems are facing multiple challenges. First, they require ultra-wide bandwidth for accurate sensing. This is because they use a time-of-flight-based method to measure soil moisture. Time of flight requires at least hundreds of megahertz bandwidth to have a reasonable accuracy. The second is a calibration challenge for EC sensing, which is caused by the attenuation method they use. So the time of flight-based method and attenuation-based method cause the overall cost of these systems to be thousands of US dollars, which is not affordable by most of the farmers. To address these challenges, we propose Strobe, a new soil sensing technique to enable accurate and low-cost soil sensing using Wi-Fi signals. It addresses the bandwidth and calibration challenges in prior work by using a multi-antenna array as the receiver, and with a novel algorithm based on relative time of flight and relative amplitude between antennas. This novel algorithm enables Strobe to use commercial Wi-Fi devices and therefore make it possible to reduce the cost from thousands of dollars to be tens of dollars or even below $10. Strobe has a simple setup with a single antenna transmitter in the air and multi-antenna receiver array buried in soil. In Strobe, we only need the channel state information reported by the Wi-Fi receiver to estimate soil moisture and EC, and then salinity. Next, we introduce details about our key ideas of using relative time of flight and relative amplitude. When using Wi-Fi devices for soil sensing, a key challenge is the limited bandwidth at Wi-Fi spectrum. We know that at 2.4 gigahertz, the Wi-Fi channels only span 70 megahertz bandwidth. At 5 gigahertz, The more than 600 MHz bandwidth seems to be promising. However, based on our experiment, the 5 GHz signals attenuate very fast in soil, so they are not appropriate for soil sensing. The remaining 70 MHz bandwidth at 2.4 GHz is very small compared to the existing RF-based methods, which use ultra-wide bandwidth. So the major challenge of using Wi-Fi devices for soil sensing is how can we achieve good accuracy with only 70 MHz bandwidth? Our idea is to use relative time of flight instead of absolute time of flight used in prior work. With an antenna array, relative time of flight refers to the time difference of wave traveling to 2 adjacent antennas. Our key insight is that the resolution of relative time of flight is not limited by bandwidth. This is because relative time of flight is estimated based on phase rotation. Its accuracy has been proved by prior work on angle rivals. So to use relative time of flight for soil moisture sensing, we first need to create the dependency of relative time of flight on soil moisture. To do so, we rely on an insight that when path differences between antennas happen in soil, relative time of flight will have a dependency on soil moisture. We want to maximize this dependency to achieve the best performance. Therefore, we made a key design decision to place the receiver antenna array in soil and only leave the transmitter in the air. Now we have built the connection between relative time of flight and soil moisture. Next, we look at how to build the relationship between relative amplitude and soil EC. Our insight is when antennas are buried in soil at different depths, they experience different amount of transmission loss. We use relative amplitude between antennas to estimate the extra transmission loss experienced by deeper antennas, and then use the extra transmission loss to compute EC. Compared to the absolute amplitude-based method, our method is much easier to calibrate. For the evaluation of Strobe, we implemented it on USRP for ground truthing with wide bandwidth and on warp and Wi-Fi card for the Wi-Fi spectrum measurement with only 70 MHz bandwidth. We first validated the accuracy of relative time of flight with over-the-air measurement. Relative time of flight can significantly outperform absolute time of flight, especially when the bandwidth is small. Next, we look at Strobe's performance in measuring soil permittivity. In our experiment, we add water into soil, and we can see Strobe can correctly detect the soil moisture increase. We compare Strobe with a commercial-grade soil sensor that costs as high as $300 US. We see a very small deviation between Strobe and the commercial-grade soil sensor. When experimenting with soils at different salinity levels, we find that Strobe can even outperform the commercial-grade soil sensor in terms of detecting different salinity levels. We also tested Strobe with real-world soil. For each soil type, Strobe can correctly detect the moisture changes. For different soil types, Strobe is able to detect their different salinity levels. To conclude, Strobe is a new soil sensing technique that enables low-cost and accurate soil sensing. Its low cost is achieved by using commercial Wi-Fi devices, and its accuracy is achieved by using a novel algorithm based on relative time of flight and amplitude. Strobe is a big step towards the adoption of data-driven agriculture by smallholder farmers. It enables a future where any farmer can use their smartphone to collect soil data. In the future, we plan to take Strobe into multiple directions. First, we want to further reduce Strobe's cost to be less than $10. We are investigating backscatter solutions and methods to increase battery life. And we are working with traditional sensor manufacturers to commercialize Strobe. We are also looking into methods to improve Strobe's capability, such as sensing deeper into soil with beamforming techniques. So for more information, you can go to the FarmBeats booth. You can go to the Microsoft booth for the FarmBeats demo and check out the link to FarmBeats. And last summer, we actually demoed our work to Bill Gates, and Bill Gates